That's not true. I ate the lunch too.
Not here.
That's nice. All right, well, welcome to the Deep Knowledge Track. I am Paul Proctor, Practical Security Inc. I am going to be monitoring this session for you guys. I want to introduce Maximiliano Caceres. I'll let him introduce his own name. That'd be much better. But anyway, he's going to talk about system call proxy.
Hello. Okay. Well, my name is Maximiliano Caceres. I work at Core Security Technologies, and I'll be speaking about Syscall Proxying today. Basically, the presentation is directed at explaining the Syscall proxying technology. What I will do, I will start with some general concepts related to Syscalls. We will go then to what Syscall proxying is, and then we'll take a look at how we can make it work, and what is it good for. So, first, some very general stuff. A process typically interacts with certain resources to accomplish a certain goal. For example, a file in a disk, the screen, or a networking card. This interaction is done through the operating system and through the what we call system calls, which are operating system services. These system services can be identified usually with the lowest layer of communication between a user mode process and the kernel itself. If we look at the most popular operating systems right now in use, we can take a look at Windows, Linux, the BSD, Solaris. And if we look at them, thinking about how do they implement these system-level services, we have two very distinct groups. One is the Unix group, and the other is the Windows. If we just look at the Unix group, we'll see that there exists an homogeneous mechanism for calling a syscall, usually identified by number. This mechanism usually is either a software interrupt, a software trap, or a far call. And usually a register is set with a syscall number we want to call. There's also a common convention used for passing arguments that are either passed through the stack or through registers or through a mix of both. Also, in the Unix world, these system services are kept to a minimum. OpenBSD, for example, has about 300 syscalls. And there's also a direct mapping between each syscall and its own wrapper in libc, for example, in this case. What does this mean? Usually, this libc wrapper, each system call implemented by the operating system has its own way of interfacing with it, and is very dependent on this operating system. So most of these OSs try to present a common interface for user mode programs so that we don't have to learn how to program in each one of them. So this interface usually is called POSIX or System 5, for example. So this libc wrapper it's a function in libc, which basically just translates between POSIX, for example, and the underlying operating system. A specific way of calling open, read, or get your entries, or whatever. So in Unix systems, usually this libc wrapper is very specific to each one and doesn't do much more than just interface between the two calling conventions. Now into Windows. The Windows system service layer can be usually referred to in books as a native API, in contrast to the Win32 API, which is a user mode library, and is not documented and not supported. It looks like Microsoft wants to have the liberty of changing the native API, and it has to from NT 2000 and XP without making user mode programs no longer functional. So it's a lot harder to actually interact directly with this interface. In contrast with the Unix world, there's also a high number of system-level services, more than 1,000. And also, the Win32 API calls that wrap these version-specific system-level services actually do a lot of stuff. So if you are directly accessing the system through system calls, you have to do a lot of work. So to keep things simple, along this speech, I'll refer to Windows syscalls as any function in any DLL available to a user mode process. So in this way, when we were talking about the native API calls are those in NTDLL. We are including them, but we're also including the whole API. So, a typical process uses certain resources to accomplish a certain goal. For example, to read a file, to calculate an average from a table or something. And the specific resources this process accesses and the kind of access it has on them defines the context onto which this process is running. So let's see a sample. If we have a process that is reading data from a file, we'll have something like this. If we are just focusing on syscalls. So the reader process will call open. The open syscall now inside the operating system kernel will communicate somehow with the disk and the file system and will return some information back, in this case a file descriptor, and the reader process will call read and will read information from the file, and it will call close and close the file, for example. This whole interaction is done through the operating system. The process never interacts directly with the specific resource. So let's just see an example. In the Unix world, we have, for example, in the Linux system, we have a tool that is called strace. I'm sure most of you are already familiar with it. Basically, what strace does is just, does it read? Fine. You can see what it says. Basically, what strace does is just, it logs to the screen each and every syscall that a given process calls. So we're going to see just a couple of simple examples.
Can you increase your font?
Sorry?
Can you increase your font size?
Yeah, sure. I'm not sure. maybe. It's better. No? No, it doesn't look good. I don't think I can increase the font size. I'm sorry. Does it look better on full screen or like that? Full screen is better? Yeah. Okay. Well, let's see, for example, which syscall's ID, the ID command calls. Well, quite a bunch. The trace tool is showing us all the syscalls that the ID process is calling. There is a lot of stuff that libc is doing, for example, like local stuff, memory map, and all that. But the actual thing we're looking for is here. Here, ID is calling the syscalls that define what it actually is good for. It's calling get UID, get UID, get EGID, and get GID to get information back from the system. Then it's writing to standard out, for example, and just calling exit. In the same way, we can see, I don't know, a cat, a simple cat just opens the file somewhere and writes to standard out. It's not so easy. Where is the open? Okay, here it is. Well, let me check. Here it is. Here it's opening the file and just reading from it and closing it and calling exit. So, let's talk about Syscall proxying. Syscall proxying will insert two new layers between the user mode process and the kernel itself, the kernel system services. These two new layers are called the Syscall stub, or the Syscall client, and the Syscall server. The Syscall client will be now the nexus between this process and the system, the operating system level services. The process will no longer be communicating with the system directly. This stub will convert these arguments, the arguments of each Syscall, to a common format. We will refer to this as marshalling. And it will build with these arguments and the Syscall we want to call a request for the Syscall server. And it will send this request to the server, will get back the response, marshal back its arguments as necessary, and return back to the caller process as if nothing happened. The Syscall server, in turn, will handle this request from the client convert arguments for each syscall from the request format to the native calling convention of the operating system, call the specified syscall, marshal back the arguments, and build a response and send it back. So the same reader process, now with the client and the Syscall client and the Syscall server layers in between, will look something like this. The process, instead of calling open, we call an open stub inside the Syscall client. This stub will marshal the arguments, for example, the file name, flags, and mode. We'll build a request. We'll send the request to the server in some way. The server will create the appropriate context for those arguments to be valid for the open in the underlying system, the open call, and we'll call it. The open will return to the server. The server will marshal back its arguments, build a response, and send it back to the client, and so on with each one of the syscalls. So, if we were to separate this Syscall client from the server, for example, by a network link, this same reader process, which was made to read a file and output to the string, for example, will now be opening a file on the remote and on a remote system instead of on the local one. It will look something like this. The reader process will communicate with the stub. The Syscall client stub will build a request, but this time it will send the request through the network. And the Syscall server will process the request, create a response, and send it back through the network. Now what has happened? We said before that the resources a process access and the kind of access it has to them defines the context onto which this process runs. So in this way, what we have done is we have changed the context of this running process without changing the process inner logic. The process still thinks it's opening a file and doing his stuff without knowing anything about remote execution, for example. So exactly what happens is this. The process accesses a remote resource instead of a local one, in this case a file. The process accesses this resource with the privilege of the remote server process, no longer the privileges of the client process, because the server process is the one actually accessing the resource. And the process doesn't know anything about remote execution at all. It was never meant to actually execute over a network. Some facts are like the original program was not modified at all, and it still conserves the same inner logic. If we had a program that, I don't know, grab the integrals from a file and calculate an average and then output it to the string, it will exactly do the same thing over the network with Syscall Proxying, because the inner logic is exactly the same. The only thing that will change is the actual resource it's accessing. So let's look at how this looks working. If we look at this drawing, it has a lot of common with, I guess, something that everybody knows, or most of you know, which is called RPC. The RPC, or remote procedure call, is a model for doing exactly this, or doing things related to Syscall Proxying. It's a client-server model. Each remote call is handled both by a client stub and a server stub. And Syscall Proxying can be trivially implemented using RPC. RPC looks a lot like Syscall Proxying. In this case, the client stub and the server stub will be exactly what the what the Syscall client and Syscall server layers are. But instead of calling any function, we will just call in Syscalls. Usually RPC implementations there are RPC implementations on most of the operating systems in use today. For example, Sun RPC. And it provides a common mechanism for doing RPC with any kind of procedure call. And basically, that's just what I described a moment ago. The client stuff and the server stuff just marshal back and forth information required for doing the actual procedure call to a common interchange format, send it through the network, and get back a response. So what are the benefits and the shortcomings of implementing Syscall proxying with RPC? Among the benefits, we can say that there's interoperability between different platforms. This is actually an RPC benefit, a benefit of most of the RPC implementations, which can work between different processors. And our benefit is that almost any procedure call can be converted to RPC. Now, if we just focus on Syscall proxying or RPC with Syscalls, we'll see that the user mode process that is accessing these Syscalls already knows a lot about the system where the server is running. In fact, they are very tightly coupled. It does not make any sense to convert back and forth from a common interchange format where you are calling your client and your server are meant to work on the same platform. So this is probably the main shortcoming of implementing Syscall proxying with RPC. In this case, both client and server will symmetrically convert back and forth from different formats unnecessarily, and provide a lot of generality that is not needed. So let's say we have a hunch that there should be some added value onto making the server really small. So that's why I'll focus for a while on optimizing the server size. So how can we do this? Let's move for a while into the Unix world. We can take a look at what's common among all the Syscalls in a Unix system. For example, there's an homogeneous way of passing arguments on the same system. Some arguments are passed as integers, or others are pointers to integers, pointers to buffers, pointers to structs. It's not very common to see Syscalls that are really complex into the data they need as input or as output. So it's pretty straightforward. Most of them just receive integers or pointers to buffers or strings. There's a common and simple mechanism for calling each one of these Syscalls. Usually it's a software interrupt, like in Intel platforms, software trap, or a far call. So how can we take advantage of this? In order to reach our goal of optimizing the server size, we will do exactly the contrary of the thin client way of thinking. We will think about fat client and thin server. Basically, we'll move all the platform-dependent code to the client. The client code will directly convert from the system, the client system calling convention, and directly into the server's format without no intermediate common format, because we saw that was one of the shortcomings of the RPC model. And it will create a request that will constitute exactly what the server needs just before calling the syscall, so that the server doesn't have to be smart at all. The server will then take advantage of this common mechanism for calling any syscall, and will do always the same. We'll see later what it is. And we will make the client completely dependent on the server's platform, which basically it already was. So now more into the implementation. This client code then has to create a request that represents exactly what the stack in the server should look like just before calling the syscall that we want. So it will create on the request the exact packet that will be on memory just before calling the system call. So thinking about that, integer arguments are trivially packed into this structure because they are passed by value. Now, pointers, that's the hard one. We are talking about a client and a server which reside on completely different systems. And in fact, they're run on completely different processes. So addresses that are valid on the client process for sure will have nothing to do with addresses that are valid on the server process. So we'll have to do something about that for syscalls that actually pass pointers from the client's process space to the server. So what we will do is we will, instead of directly passing the pointer that the application uses to call the client stuff, we will relocate the buffer inside the request itself and create a pointer inside that buffer. So it should look something like this. This is a sample for the open syscall. Open takes 3 arguments: a file name, flags for the open, and the mode in case you are creating a file. So the flags and the mode arguments are just integers. They can be passed by value. There's no problem with that. Now, the file name. The file name is a pointer to a string. The pointer that the file reader program passed to open doesn't mean nothing in the server memory. So you have to change that. So what we will do is we will copy the buffer that the reader process passed to the open call inside the syscall stub inside the request itself, and we will create a pointer back from the request inside itself. It will look something like this. The block on the left is exactly what the request looks like, the request from the client to the server to execute the open call. And the server, which is not as smart at all, will just copy the exact request onto its stack and call the syscall. So the stack will look exactly the same, as if the server process will have called a libc function for open. There's another detail, that is that this pointer to the file name buffer has to be an actual pointer. It cannot be like an offset into the buffer. If it were an offset into the buffer, the server call will have to be in place to change that and make it look like a real pointer. So we'll have to increase the server size to do that. So we'll see, I think it's the next slide. No, not yet. We'll see that the client will need a way to tell how the server's memory look. So the servers will, upon connection, the server will send back the stack pointer so that we can create our own virtual pointers from the client side into the stack. So a file name will be a pointer relative to that ESP or the stack pointer on the server. So, how does it look when we call a syscall in Linux? Linux is pretty straightforward. EAX is loaded with a syscall number. For example, I think it's 3 for open, but it's what we saw on the trace. Arguments are passed through the EBX, ECX, CDX, ESI, and EDI registers. Syscall that have more than 5 arguments push the rest of them on the stack. And then software interrupt 8 is called, and the return values in EAX. It's pretty simple. So if we were debugging an open call, it will look like this. We are just inside the breakpoint in the libc wrapper for open. That was what I was referring before. This libc wrapper has to change between what we just explained about how to call a syscall and what a typical user program uses to pass arguments to a libc function. In this case, they are passed through a stack. So that's what we see on the first 3 instructions. Where all each parameter is moving to its respective register. Then 5 is moving to EAX. 5 is the number of open. And then in8 is called, and that's it. So this is how our simple Linux server for Syscall will look like. First, it will set up communication with the client. That could be anything. That could be open a socket and connect, or accept connections, or whatever. Then, upon connection, the first thing it will do, it will send back ESP, like we said, so the client can build the request it needs with the correct pointers. And then, for each request, we'll just copy the exact request into the stack, pop the registers it needs for the arguments, and call the system call. This is why it's important, all the effort we did before, to actually make the request look like something that could be in a process stack. After that, we'll just push the return value and send back the buffer with the response. Why do we send back the buffer? Because certain syscalls return information on the buffers that we send. So if we're calling read, for example, it will look something like this, but instead of passing an input buffer like this, we will pass an output buffer where the read syscall can copy information. So when calling read, this buffer in the request will not make sense other than saving space for the information when it gets back. When the server calls the read system call, it will copy the information into that buffer, and then our server will send that back to us so that we can use it. And that's why the whole request packet transforms itself into a response and is sent back to the client. Some important parts of the server where we read into the stack, where the server reads the request from the client. It's basically just a call into read, but the most important thing is that the buffer or the pointer for the read is just ESP directly, so that we don't have to do anything complex with that. And invoke, when the server wants to invoke the desired syscall, it just pops the registers and calls in80, because the buffers are already in place. So just to remember that the request was previously stored in ESP, and is exactly how the stack should look before calling a Syscall. And in other systems, like for example BSD, where Syscalls are passed by the stack itself, you don't need this step. You just call in 80 after the read. So we'll see now that it's very easy to call this to implement this Syscall server. And for example, in Linux, it's just about 100 bytes long, using the SYN server fat client thing. Let's take a look at that. I have here this sample server, which you can see. It's very simple. Also, at the end of the presentation, I haven't these samples ready for the CD. But if you look at the CD, you will find that there's a paper, which is this presentation with more detail. And there's also all this. There are also these samples on the net. I'm going to pass you the URL at the end. This is basically what we've been talking about. The server just reads the request, calls the Syscall, and sends the answer back. It's pretty small. And what we do here is we just accept new connections from a socket to have some kind of communication channel with the client. Among these samples, I have a simple client for this server written in Python, which I'm going to use for demonstrating how this thing works. And here I have this is a Red Hat Linux running on VMware. I just executed the Syscall server inside strace, so we can see how the things that we do from the client show up in the server. So here it goes. As we said before, the first thing that the server does once the client connects is send back its stack pointer so that the client knows how to package the request with the buffers. And now the server is blocked on read, waiting for new requests. So we can call ID, for example. This is how it looks. The two reads here are the actual requests from the client. This is the client was calling get user ID. This is the actual request. Get UID return 501, and the server write back the response, and so on for the other Syscall. So we can call, I don't know, get current working directory. It's even easier. It's just one Syscall. This is one Syscall that, for example, returns information back in a buffer. We can call exit, which just kill the server program. There you go, exit 1. So, what happened to Windows? Before we said that we will simplify and we will call Windows Syscalls any function in any DLL. Well, there's a common mechanism for calling those. So our simple Windows server cannot simply call in 80. So we will create, to make it simple, we'll create a server that just calls any address that we give him. So if we do that, we will be able to call any function on any DLL that is already loaded into the server process, and that's it. But there's one more detail, that is that the blob library call and the getproc address call are already part of this address space. So we can call them and actually load new libraries into the system. So this is how the pseudocode for the Windows server will look like. Again, it will set up a communication. It will send back ESP. Two new things happen. It will send back the address of the library and the address of getproc address. And then it will simply loop into a request reading loop in which it will just push the whole request into the stack like before. And this time, it's even better because DLL calling convention in Windows passes all the arguments into the stack. It will pop the address of the function I want to call, and it will just call it and send back the response. So in this way, the client can tell the server to call any function that it wants, and also make the server load new libraries and get the addresses of new functions to call. The only thing that is a little more difficult is the request packing code, because now we are trying to make every call possible. So functions, Win32 functions, for example, have some funky structures that are nasty to pack because they point back into itself and that kind of thing. So that's the client code is a little more complex, but the server can be really small too. So what is this good for? Basically, any task related to remote execution could be done with Syscall Proxying, but the fact is that this fat client scene server architecture lags behind RPC for generic stuff in things like efficiency and interoperability. But there's one use for what this thing is good for, which is for exploiting code injection vulnerabilities, like buffer overflows and format strings. So what are these things? Usually, these kind of vulnerabilities give the attacker the ability to gain control of the processor in the target machine, and usually they are attacked in this way. The attack can be divided in two stages, which is not new. There's an injection mechanism, which is specific to the vulnerability, which basically tries to gain control of the system, tries to gain control of the instruction pointer in the remote system. And then there's a payload, which is the actual code that we want to execute once we have accomplished that. So usually we see something that is called shellcode, that is basically code that using Syscalls spawn a shell on the remote system and send it back to the attacker's machine. So the attacker now has an interactive console of the target system. Let's see what happens when we do that. Suppose we are doing a penetration test, for example, and we have successfully attacked the host, and now we have a shell. Now we have two options. Either that's it, and we hit our final target, and we are happy, and we open a beer, or we still need to keep on working, right? So what do we do with this new system that we have? We either keep trying attacking our system from where we were before, or we try to move there and take advantage of being inside the victim's network. If we could do that, we will absorb the privileges of this application that we just exploit. In this way, we could exploit webs of trust between different systems. We could bypass a firewall, for example, because we will be already inside. And we will have effectively changed our profile from one of an external attacker to one of an internal attacker in this case. So this is what we refer to as pivoting. To be able to actually take advantage of this new advantage point inside the system, the auditor is faced with a problem, which is if we want to keep attacking systems from there, we need our tools there to work. So I'm sure most of the people that have done penetration testing here has been faced with this problem. I have I have just hacked into a Windows NT box, and now I want to keep going, and I found out that all my exploits are for Linux. So now I have a problem. I either have to do it again, or I cannot use the system at all. Other problem is that, I don't know, I have attacked a Linux box, but it is a different version of libc. So I have to upload libc, build libc. Ouch, I don't have CC, I don't have a compiler. I have to upload the compiler, build the compiler, build libc, build my tools, go ahead. And that's not something nice. And it also makes the task of leaving everything as it was before very complex. So this is where Syscall Proxying comes in. What we are proposing here is, instead of using a generic shellcode for payload for attacks, we will supply this scene server, which is actually as small as a shellcode. And that's why we wanted initially to make it small. So what are the benefits of doing this? First, if we build all our tools with Syscall Proxying, once we have deployed a Syscall server on a system, now we have all our tools there too. So we can pivot on them without doing nothing, without changing our exploits or information gathering tools, etc. We have complete access to the target system, so we can try to escalate privileges locally, for example, exploiting a local vulnerability to the system, or bypassing certain, excuse me, bypassing certain constraints that the vulnerable service has done to lessen the impact of an attack. For example, lowering privileges after authentication, running inside a change root jail, etc. And the other important benefit is that sometimes, even though a given service is vulnerable to an attack, it's not possible to spawn a shell. Because we are, for example, inside a change root jail where there's no shell at all. So even though the vulnerability exists and we could take advantage of that, we are not able to do it. So if we can deploy a Syscall server then there, we might not be able to escalate privileges locally, but we might be able to launch attacks from this system, even though there's no shell. So before this, I have a simple example that is the same server, but it basically lowers the privileges, change routes to /TMP, and changes the effective ID of the process to nobody. So I'm gonna connect to this same server now, the same I did before, but I will run a sample that will basically get back the privileges of the super user and get out of the chain root jail. So this is also something good about Syscall Proxying. It gives the attacker the ability to, once it's got in, take a look around and see what's going on. For example, in this case, I'm calling get UID and get EUID and get current working directory, and I'm doing an ls, and I realize that I'm inside the chain root jail because there's no way what I'm seeing is root. And I'm not root because the process lowered the effective privileges of the user. This scenario is exactly what happens when you exploit a vulnerability in WFTPD, for example. WFTPD will do exactly this. Will change root to /home FTP and call set UID with the ID of the user you authenticated as, for example, anonymous or whatever. So if you actually, if this were an attack against WFTPD, we'll see the same thing. So what happens then? You either don't do nothing else, or you change your attack to accommodate for this. This will require, for example, a shellcode change to call set UID 0 just before spawning the shell. In this case, I can do it interactively because I'm not talking to a shell. I'm talking to a Syscall server. So now I change my ID, and now I can break out of the chain root with some common mechanism that exists to do that once you are root. So now I'm there. If I didn't have Syscall Proxying, I could have done the same thing, but I will have to put everything inside the payload I'm sending. So I will have to change my shellcode, and I will have to not only have multiple versions of shellcode for different operating systems, but also multiple versions of shellcode for different configurations. Like if I have to call setUID, if I have to get out of a chain root jail, or if I have to find out a socket, or whatever. So, wrapping up. Syscall Proxying can be a really powerful technique when attacking code injection vulnerabilities. It basically instantly turns the compromised system into a vantage point from which we can stage further attacks into the system. And it's also useful when shellcode customization is needed because the process set up some constraints. And it could be also a powerful framework for developing penetration testing tools. If we had all tools developed with Syscall Proxying in mind, we can take advantage of having our attacks deploy a Syscall server, and we will be able to jump from them very easily. So coding with Syscall proxying in mind basically raises the value of these tools. That's it. Do you have any questions?
Could you explain a little bit more about your example? The commands that you're typing, ID, DVD,
Yes.
they're written in Python, I assume.
Yes.
Could you explain a little bit about that?
Yes. Basically, I'm not exactly, this is what's going on. I have a Syscall client written in Python, which is built like a library. And then on top of that, I have just this mini shell script that basically uses that model to call syscalls. So for example, if I call cat, this is actually more than one syscall. It's calling open, read, close. So it's more complex than that. We can take a look at it. This is the mini shell source. Every time I type a command, one of these methods is called. So for example, when I type ID, I'm telling my client to call get UID and get EUID for, I don't know, cat. Here it is. First I get a file descriptor calling open, then another one calling read, and I don't close the file, which is not nice. We can take a look at the proxy if you want, but let me see. I think this will be useful. I'll manually call the functions instead of using the mini shell, which is handy for the demonstration, but it's kind of it's a layer on top of it. I have connected to the client, to the server. And then I can, this client, you can take a look here at it, basically implements a generic method for calling any syscall in a Linux system, which is this method. It self-explains a lot. Builds a request with a syscall number, which is the first register we pop, and then packs the arguments inside the request, sends the request, gets back the response, and unpacks the return code, and that's it. So for example, here I have the get current working directory syscall. It basically just creates the arguments for the syscall, which are like a buffer and a length. Calls the generic syscall method, unpacks the return buffer, and sends back the response. We can call that. Here is the call to the syscall. So I guess the Syscall client is pretty simple. There's only there's one method that does everything from which you can call any Syscall, and then there's some common Syscall that I use on this demonstration that are already implemented, but then it's very easy to just do it manually. You're welcome. Something else. You can find this the presentation, the paper, and the server for Linux and the Python client libraries in this URL. I think they should be there right now, but it might take, maybe they are there tomorrow. So just if you don't find it, just check again. I know. Have other questions? What?
You're at the Windows server also?
No, there's another sample for that. No, it's just the pseudocode. Yes?
URL yet?
What? Sorry? URL again. I'm sorry. Here.
Is there a way to distinguish between which calls should be made locally and which calls should be made on the server? For example, you open a local libc and a remote etc password in the same program.
You mean if there's a way to distinguish from a given program which ones should be executed locally, or if, well, that's not easy. Yeah, it depends a lot of what are you looking at. There are some stuff that can be done with Syscall Proxying. I mean, initially, Syscall Proxying presents itself as a way of putting a process, making the process execute remotely without the process knowing anything about it. So thinking about that, we are talking about running everything on the remote server. But sometimes there are other stuff that you can do. For example, you could use a Syscall server to do a file transfer, because you could open a local file and open a remote file, and then read and write from one and from the other one, which is something that looks kind of, it's not the same thing we're seeing here, because you will have to call like a non-Syscall proxy that open, read, and close, and a Syscall proxy that open, read, and close. So with the first, you will open the local file and read from it, and with the second, you will open the remote file in the remote system and write to it. So if you just want to make one process execute remotely, I think you will have to select which ones you want to actually proxy. You don't want to proxy memory management Syscalls, for example.
Can you Syscall proxy something like Nmap?
Yes, of course. Well, I won't say of course. You could Syscall proxy everything that Nmap does with system-level services. For example, using raw sockets. But if Nmap uses pickup, you will have to communicate directly with BPF on the remote system. Or you can change pickup to use Syscall proxy, the lib pickup, so you can rebuild Nmap with that. There are some other interesting stuff like DLL injection and dynamic library. I don't remember the name of the paper. Some guys that are doing some stuff with changing what dynamic libraries a process opens and putting themselves in between. So that's another approach to Syscall proxy a process without changing nothing. The approach I'm showing here is I'm not calling the actual libc functions, I'm calling another library. So you will have to rebuild the tool, for example, Nmap. I think it should be possible to inject in the DLLs and make Nmap go to a Syscall proxying scheme, but I think it will be delicate for some things.
You know when I'll put in that Dropbox situation in the end, so you want to just go Proxying and
Yeah,
upload it over.
yeah, of course. That's what this is about. Yeah. I think it can be done, but I'm sure it can be trivially done for the stuff that uses raw sockets. It might be not so trivial for the BPF stuff, for the packet capture. Yes.
Well, as it's good right now, is it determined that the packet platform or the Syscall client use the same architecture and the same operating system as
It's a server.
the vulnerable?
The sample that is going to be there, yes, it takes advantage of that to make the server simple, right? So yes, the client is completely dependent on the server's platform. There's something more that can be done. You can build another layer of abstraction on top of the Syscall client, something like libc, which basically will translate back and forth from these two different schemes. So it should be a way of making any POSIX compliant code be able to be Syscall proxied on any server, for example. But you have to take an extra step and build that abstraction layer on top of the Syscall client. These are like the Syscall client and server that I presented here are like the lowest layer of it. So yes, it's very dependent, I think. And we are out of time.
Server. You said it's 100 bytes.